take a spacecraft and you just slam it into the asteroid. And by slamming it into the asteroid, you give it a push.
Of course, the first time we discussed it, we were saying, oh my God, we really need to check and double check and make really sure.
Hello, I'm Daniel Skuka from the European Space Agency.
And I'm Tanya Johnston from the European Southern Observatory.
And today is
Asteroid Day.
Tanya,
Finally here.
Finally, it's here. Welcome to Asteroid Day here at ESA Supernova in Garching. And we have a fabulous webcast program planned for the next 2 hours.
Yep.
It's a joint production between ESA and ESO. And Tanya, can you give our viewers a little bit of an idea as to what we're going to see in our program today?
Sure, so we've got a fantastic lineup of a range of people that will be interviewed. So we've got from ESO, we've got Dr. Susie Ramsey who will be on talking to us about ESO and the telescopes and how they're used for asteroid detections. And also we've got some fantastic interviews with Ollie Henno, our in-house asteroid expert.
Good stuff. Coming over from the ESA side, it is a joint production. We have Detlef Koschny, who is the head of the Asteroid Program Office. We have Timur Prusti, who is our Gaia mission scientist. It's a fabulous mission, and it actually has a lot to do with asteroids. We actually have Con Kayal coming to us from the DLR, the German Aerospace Center in Cologne. He is working as on part of the mission operations team for the Mascot lander, which right now is still attached to the Hayabusa 2 spacecraft, which just this week arrived at an asteroid Ryugu, and in just a few months that lander is going to actually touch down onto the surface of the asteroid, so that's totally exciting. And we have Olga Popova, who is a Russian scientist, and of course our connection with Russia was very clear.
Yep.
Chelyabinsk, 5 years ago this year, in February, was the Chelyabinsk asteroid event. It was the most significant event happening, well, in the past 100 years.
More recent, because there's another one which is also pretty spectacular for this particular day. So the Tunguska event.
Tunguska was in
fact,
it's
110.
110 years, exactly, 110 years ago today. And that's why we're celebrating Asteroid Day today. Asteroid Day is?
It's an international awareness day to let people know what organisations like ESA and ESO do to help us to detect asteroids and tell people more about them and how they're behaving so that we can hopefully prevent impacts in the future.
Right. Now, as you're watching today, we want you to, if you've got some questions in our program, something that piques your curiosity, if you've got a question you'd like to ask to one of our experts, you can actually use social media to tweet. You can use the Ask ESA hashtag.
Or Ask ESO.
And we've got some of our colleagues are looking at those hashtags, and when we see your questions, we'll actually put them all together in a list, and we can't promise to answer all of them, but we'll certainly pick some of the best ones and see if some of our experts here today can answer those.
What are you most looking forward to today, Daniel?
I am most looking forward to a new revelation coming from the European Space Agency, of course. Many people believe that the dinosaurs were wiped out 65 million years ago in a stupendous asteroid impact, and that's mostly true. However, we've done some research, and we're going to show you a video clip a little bit later on in our program that investigates exactly why the dinosaurs went extinct. And indeed, some people are not totally certain that the dinosaurs are extinct. If you, out there watching our program, happen to see a dinosaur right here in ESO Supernova, we'd like to know about it.
I need to know if there's a dinosaur roaming around in the ESO Supernova.
Absolutely. If you see a dinosaur in our program today, we'd like you to get a screenshot, grab a photo with your phone, tweet it, post it on Facebook, use a hashtag
Spot Sophia.
If you see a dinosaur, use the Spot Sophia hashtag. Right, ESO Supernova. Tanya, tell us about this fabulous planetarium.
So this is an amazing facility. We've only been open for 2 months. It's right here in Garching, just north of Munich. And it's a planetarium and visitor centre, and obviously that means we have a planetarium, but we also have an exhibition, which is huge with loads of information about astronomy. The building is run by ESO, and it was a donation from the Klaus Tschira Stiftung. And it's a really just fantastic facility, and since we've opened we've had more than 15,000 visitors so far, so it's been really busy.
That's great.
And yeah, I mean, we can take a look at a video that gives you an idea of the building as well, because the architecture is spectacular. So the building design is actually designed to look like a binary star system, which is two stars are sort of merging, which leads to a supernova, hence the name.
And a supernova is a ginormous explosion.
Yeah, sort of explosion of stars. And one way it happens is that stars transfer mass to each other. We're right here on the campus, the research campus in this university city of Garching, just north of Munich. We're right next to the headquarters of the European Southern Observatory, so we've got that direct link with ESO, but also on the campus we have loads of other institutes that are doing fantastic research in all sorts of fields. So we've got some colleagues from other institutes here today to talk to our visitors about asteroids as well. And yeah, as I say, you're seeing a video that shows you a bit more about the activities. We've got a huge schools program. And in our exhibition, one of the coolest things I think we have, especially in light of today, one of the coolest things we have is a real meteorite. So when I say meteorite is a rock which has been found on Earth, but it's come from space, typically from an asteroid. And we have two meteorites on display in our exhibition, one of which is a very special meteorite. So it's called the Vaca Muerta meteorite. And Vaca Muerta is actually the place where the meteorite was found, means dead cow. So we're saying that this is actually a zoom on the meteorite itself. I don't know why it's called dead cow, but that's the name of the place. And so we have this meteorite that visitors can see firsthand and really study it. So if you're around and want to come to the supernova, it's one of the many things you can see here in the building.
Now, for our audience, if you're in the Munich area and you pass by ESA Supernova, indeed, a lot of the content is in German, but you're actually bilingual with English as well.
Fully bilingual. So the centre is fully bilingual because ESO is an international organisation. Our working language is English, but of course we're based here in Germany, so we're going to have lots of local visitors. So everything in the exhibition is provided in both English and German. All of our shows in the planetarium, we show them both in English and in German, and our activities are available both languages as well.
Right. Last minute, quickie, you've been overseeing Supernova here since it started. You just opened in April. What's the most fun thing you've got here?
The most fun thing, obviously the planetarium is a big draw, but we actually have a piece of the Atacama Desert here. So the Atacama Desert is very special to us. So the Atacama Desert is in Chile, which is actually where that Vaca Muerta meteorite was found, and that is also where our telescopes are. So people can actually visit the Atacama Desert here in the supernova.
Good stuff. If you're in the area, pass by ESA Supernova now or anytime in the future. Tanya, in today's webcast, we're talking about asteroids, and we've got a number of specialists joining us here in our webcast. They're going to be talking about some fairly scientific, complex scientific terms: asteroids and meteors and meteorites and NEOs, near Earth objects. This is very confusing for some people.
Yeah, so we took the opportunity to speak to Olli Heno, our in-house asteroid expert, to find out, well, to get his definitions of some of these terms, and we can take a look at the video now.
Okay, let's go to the video with Olli.
Near Earth objects are really just that. These are celestial objects that come near to the Earth, and there are broadly two classes: near Earth asteroids and comets. The near-Earth asteroids, they mostly come from the asteroid main belt, which is between Mars and Jupiter. And it can happen that because of a collision or because of an interaction with one of the planets, one of them falls down from its orbit in the main belt to an orbit that brings it closer to the Sun and therefore closer to the Earth. The near-Earth objects, there are a few big ones, there are many more small ones, and there are many, many more very small ones. We know most of the big ones. Big is 1 kilometer or more. For those that are 100 meters, we know about 10%. For those that are 10 meters, we know less than 1% of them. And so that's annoying, because an object that is 10 meters in diameter on impact with the Earth would release about the same energy as a Hiroshima bomb. We are trying to characterize everything that is bigger than 20 or 50 or 100 meters, where we are at 10% now, so we still need to find 90%. In terms of numbers, we know 10, 20,000 of them, and we are still missing 90%. So there is a lot of work to find them and to track them. To discover near-Earth objects, you need a super wide-angle telescope. And then you just scan the whole sky, night after night, in order to see everything that is moving. The asteroids are moving, and so we have a computer program that will find them, measure their position, and from this position we can extrapolate the orbit, and we refine the orbit until we have an orbit that is good enough that we will not lose the asteroid again. We know from history and also looking at the moon that there are many impacts. On average, a small one, which is like a few tens of meters, that happens every few years. Bigger ones are fortunately less frequent because there are fewer of these objects. Very big ones are even less frequent because there are very, very few of them. So if you take a very big one, like 15 or 20 kilometer asteroids hitting the Earth. Last one was 65 million years ago. That was bad for the dinosaurs. And historically, we see this kind of giant impact every 50 million years or so. To predict an impact with a near-Earth asteroid, a near-Earth object, you need to know its orbit very precisely. And so to do that, you need to measure the position of the object on the sky over and over and over. It's difficult because many of these objects are small and they are not always near the Earth. They can be on the other side of the solar system. And the combination of their size and their distance makes them extremely faint, which means that most of the time the telescope that discovered them, which is 2-meter class telescope, can observe them only for a few days, and then they cannot see them anymore because they become too faint. And that's where the VLT, the 8-meter big telescope, come into play, because with the collecting power of a huge mirror, we can see much fainter asteroids. Using the VLT, we refine the orbit of the near-Earth objects, the threatening ones, those that could have a collision, in order to make sure that the orbit is known well enough, either to rule out a collision, that's ideal, or to characterize a collision. To protect ourselves from a near-Earth object, we must know them and prepare in advance before a collision. So if we have enough time, 20 years or so, we can send a rocket and do something to the asteroid. That can be nuke it, atomic bomb, either to try to destroy it or to push it. Or there are some more gentle ways. A cute way to do it is to spray paint the asteroid with bright white paint, because that will change the way it reflects the sunlight, and that can be sufficient to push it away from its orbit. Or you could also land a small rocket on the asteroid and let this small rocket push it. Or if it's a very small asteroid, you can go cast a net, grab it and pull it away.
Welcome back to the ESA co-produced Asteroid Day webcast. I'm Daniel Skuka. I'm speaking now with Detlef Koschny, who is responsible for asteroid activities within ESA's asteroid program. Detlef, thank you very much for joining us today.
You're quite welcome.
Detlef, at ESA we actually have a team of people who are looking at asteroids. They're studying them, they're actually tracking them, they're trying to come up with predictions as to what their orbits are. Tell us a little bit about what's happening at ESA's NEO Coordination Center.
At this NEO Coordination Center, we collect information of all the observations of asteroids and predict their orbits 100 years into the future. In particular, we look at whether an asteroid could possibly hit our planet.
Now this actually happens quite frequently. Of course, they're very small, and indeed we had an event just earlier this month over South Africa, over Botswana.
That's correct. This was really a fascinating thing for me, but for the complete team here. We had a few weeks ago on a Saturday, we were able to observe an asteroid which would impact our planet only 8.5 hours later. That's a bit late, actually. Now, this object was quite small, so it was not a problem. But we'll discuss later, for example, the telescopes that we use to search for these objects. We need these telescopes to maybe have a bit more time to warn whoever is below the impact.
Right, we had a chance actually to visit ESA's NEO Coordination Center in Italy and speak with the team that were working on that particular asteroid sighting earlier this month. Let's go to the video.
Hi, I'm Kelsey Brennan-Wessels for ESA Web TV. Here at ESA's Esrin establishment just outside of Rome is the seat of the Near Earth Objects Coordination Center, or NEOCC. At the beginning of June 2018, a fireball was seen in the sky above Botswana, just mere hours after the asteroid was discovered. This was the third asteroid in 20 years that had been detected before entering Earth's atmosphere, putting teams like NEOCC through their paces. They told us more.
On the 2nd of June, an asteroid measuring between 2 and 5 meters was detected by an automated system that is running in US, in Arizona. And this object was determined to have a trajectory, a colliding trajectory with Earth with high accuracy. So at that immediately, the planetary defense community was activated in order to try to ascertain with high accuracy whether this object was going to collide or not, and where. Immediately, the system informs a number of people such that they can get into action and request more observations in order to determine the trajectory of this object. Within that persons, our colleague Marco Micheli at the NEO Coordination Center at ESA was called in order to perform more measurements and be able to make a better computation of the trajectory of this object. This is a extreme case because usually what we do is we have more time to react. We usually, the automated systems usually detect the asteroids. Then, this is where we come in, there is the need to follow up in order to get more observations of this object. All those observations together are used by orbit determination software that we run in order to determine with the maximum possible accuracy the trajectory of this object. And once we have that trajectory, what we do with other tools is to calculate the projection of the orbit and then see whether it would impact with Earth anytime in the next 100 years.
Marta Ceccaroni is a celestial mechanic, a type of astronomer that deals with the motions of objects in space. She told us more about how NEOCC monitors and communicates about objects at risk of hitting Earth.
The normal process when an asteroid gets discovered is that this survey telescope sends data to the Minor Planet Center, and the Minor Planet Center waits to verify that it's actually an asteroid, then sends out the data, and here is exactly where the NEOCC comes into the game. We evaluate the orbit of the asteroid, and then together with our twin system in Pisa, we evaluate if there is an impact probability, and so if there is any chance that it's going to hit the Earth. Of course, we have some parameters to measure the risk in case there is, and with those parameters, it is compulsory for us to phone to the JPL and to compare the data to see if we agree on our evaluations. And then if we agree, it goes directly online. So it gets published and everything is absolutely public. Is in our website, there is a risk list in which there is the list of all the asteroids that have got an impact probability that is major than 0.
So today we have 746
that have an impact probability more than 0. But most of them is a very small probability. You can see that they are not very worrying, or the time it's really in a long time they're going to impact, because of course we also have the data of the impact. So of course what we have to do is not only to evaluate the risk, but we can also, like for example what happened for 2018 LA, we also evaluated all the close approaches, so the orbit, and we see that it has been with us for a long while, just passing by every now and then. And then actually in the end it was hitting the Earth and we were evaluating all that part. Other things that we have is that in case of an impact we evaluate the impact corridor of the object. So of course there is a probability, and it's not that we know for sure where exactly it's going to hit, but we've got layers of probability. And of course we both evaluate where it's going to be at the altitude of 100 kilometers and then at 0 level, so where it's going to impact. And in this case we were forecasting that it was going to hit in Botswana.
An event like the 2018 LA asteroid doesn't happen every day, and while this fortunately didn't cause any damage, it was a good example for the NEOCC to see how they contribute to planetary defense and how improvements will be made in the future.
This type of events are something that we want to see. It actually let us see that we are contributing to protecting our communities, and that we are little by little improving our systems such that we, in the near future, will be able to, once that the Fly-Eye telescope is in place, we will be able to detect this more often and be aware of the threats that come from the sky.
You can check out the latest news from NEOCC and their risk list by going to the website neo.ssa.esa.int. I'm Kelsey Brennan-Wessels for ESA Web TV. Thanks for watching.
And we're back for Asteroid Day with the European Space Agency and the European Southern Observatory, live here from ESA Supernova in Garching, Germany. Remember, as you're watching today's program, if you have a question, you can tweet it, you can post it, you can Facebook it in social media using the hashtag AskESA or AskESO, and we'll try to answer the best of those questions within our program. We're here with Detlef Koschny. And Detlef, we are working on a number of ways to look for asteroids in the sky, but moreover, we're also looking at meteorites that end up on the surface that come through our atmosphere. And just last night, we had a fireball, an entering piece of space object coming through the atmosphere over Holland. Tell us a little bit about what we're doing to look for objects coming through the atmosphere.
Yeah, that's correct, Daniel. We have a project called FRIPRON, which was initiated by a group of French scientists. It's a network of cameras, fisheye cameras, that look at the complete night sky, every night, and they look for bright fireballs in the sky. So this is not a warning system. It just tells us, oh, there was an object right now. That's scientifically very interesting. We can find the meteorites after the object fell down and link that to the asteroid.
We had a chance just a couple of weeks ago to ask Sean Blair from ESA Communications, ESA Web TV, to actually have a visit with the team at Aztec who's working on the FRIPRON camera and find out a little bit more about the FRIPRON network.
Hello, I'm Sean Blair for ESA Web TV, and I'm here in Aztec in the Netherlands, which is the technical heart of the European Space Agency. This is the place where engineers and scientists develop the new technologies and missions that are going to go out and explore the solar system. And then once in a while, a little bit of the solar system comes back to visit us. That was footage of a fireball passing over Aztec. And actually, there have been half a dozen fireballs that we've recorded passing over the technical center in the last year. So let's go find out a little bit more about them. I'm here now in the offices of ESTEC's Meteor Research Group with science trainee Christiana Smit, who's researching fireballs and meteors. What made the picture, the footage we just saw?
So we've got a fireball recording camera just on top of the roof of ESTEC. And this camera is part of a network of nearly 100 cameras spread all over Europe. And it belongs to the FRIPON network.
And what does FRIPON stand for?
FRIPON is the Fireball Recovery and Interplanetary Observation Network.
And recovery, that means that you're not just looking at them, the idea is to actually track them down.
Yeah, that's the point. So if we've got not just one camera observing the fireballs, but 2 or more cameras, we can find out about the orbit and the trajectory of the fireballs. And then we can figure out, okay, where did the meteoroid land on the Earth, and figure out what's the composition, find it. That's the goal.
Where is the camera exactly?
It's right here on top of the roof.
All right, well, let's go take a look. Well, I'm up here now on the very top of ESTEC to track down the FRIPON camera, and here it is. And I'm up here with senior data technician Andrea Toni, whose job it is to maintain the FRIPON and the system behind it. Well, Andrea, the camera itself is quite small and compact. What's actually inside it?
Yes, the camera is quite small. There is a CCD on top, which is taking images, 30 frames per second. And inside there is an Ethernet controller, which with just one cable and the power is sending down the images to a computer, which is recording 45 days of data. The look of the camera is fisheye, so you can cover 180 degrees. And yeah, this camera has been here for 1 year and a few months. And we already got 6 detections with them. This is a French project, and it started in France, and they have already more than 100 cameras in France. Here in Holland we started just last year. We have 1 here, 1 in Oostkappel, but we do plan to expand, of course.
And what's the advantage of having more and more cameras? What does the project get out of it?
Well, the geographical coverage of one camera is an area of around 100 kilometers. So if you really want to have multiple detection and cover a big surface, you need one every 100 kilometers. So for Holland, we plan to install 8 more. It's very nice when we have multiple detections, because then we can compute the trajectory and the orbit in a better way, and it's easier to see if it's something which is fall down on Earth, where the position is.
So that's the real goal, to actually one day find something based on the camera detections?
Yes, indeed. It's very nice to find something, to see the structure of whatever fell from the sky, to see how it is made and composed, and try to understand how these meteorites or fireball are made of.
So that hasn't happened yet, but that is the long-term goal of the project?
Yes, indeed. Not yet in the Netherlands, but we are looking forward to get more of them.
Well, fingers crossed and best of luck. I think we'll go down now. The nearest neighbour to ESTEC's fireball hunting camera is about 80 kilometres away as the crow flies in the westerly Dutch province of Zeeland. We've come here to take a look. We're standing now in the small Dutch village of Oostkappel, close to the sea. So this FRIPON camera's in a very different setting. This farm belongs to Klaus Jobser, who's taken advantage of the dark skies around Zeeland to devote his farm for amateur astronomy. It's called the Cyclops Observatory, and it's a well-established part of the Dutch astronomical landscape. And since last year, among his other cameras and telescopes, he's also been hosting a FRIPON camera here. And you've been a keen amateur astronomer for a long time.
Yes, that's true. I've been amateur astronomer about 50 years now, and well, I've always lived in this area. Quite dark sky. You can see the Milky Way with the naked eye, so it was easy to get involved. And
asteroid observation is one area where amateur observations are very important.
Yes, that's true, because on a quite simple way you can collect data, scientific valuable data, with the telescopes. I'm an amateur, so it should be fun, but it's also a bonus to have some data which can be shared with the scientific community.
In the background here we have a fair few cameras. There's this big telescope here, there's the FRIPON. You also have these smaller cameras here. So what are the other cameras for?
The other cameras are part of the CAMS network in the Netherlands and in Belgium. They film and photograph smaller meteors So not the big particles which Freeport is aiming at, but the more smaller ones. And we have a network in the Netherlands and in Belgium, and collecting quite a lot of meteors every night.
What do you yourself have to do with the camera?
Well, very little. I have to provide power and good space, and then the data goes directly to Marseille. And when there is a good event, I get the data back from France.
Oh, right. And they're looking to expand the network further. Would you encourage other people to maybe see if they can get involved with FRIPON?
Oh yes, certainly. The more stations, the better for a good coverage of the sky above the Netherlands. So it's very good to have more stations, yes.
Well, thanks a lot for showing us around. This is Sean Blair for ESA Web TV, signing off.
Which are scanning the skies, looking for asteroids, and sometimes we make amazingly exciting discoveries, things which are not even in our solar system. And in the last year we had one such discovery, and Detlef was co-author on the paper about the discovery of this object Oumuamua. Apologies to any Hawaiian people if I've said that wrong. But Detlef, tell us about Oumuamua, and in particular what we've just recently discovered about it.
Right, yeah, that's really an exciting object, and it was discovered last year, and we recently published the second paper. That's where I was involved a bit, and we found out, initially people thought it's an asteroid because it didn't look like a comet at all, which people would expect. We have found out in the paper that it is a comet after all, and that's a super exciting discovery.
So how did you find out it was a comet? What was it that told you that?
What happens is comets are outgassing, and that means they generate gas, and that gas pushes the comet away a bit from the orbit you would expect it to have if only gravity were working. And that's something we can observe using large telescopes, using the Hubble Space Telescope. So
it's a bit like cometary flatulence.
I think that's the term, yes, that's the medical term.
I thought so too. It sounds like a very technical term. Ollie Hinault from ESO was also involved in the work on Oumuamua, and we had the chance to interview him about it as well, so we can take a look at the video clip
Let's
now.
have a look.
In 2017, astronomers discovered Oumuamua, the first interstellar object in our solar system. Now several telescopes, including ESO's Very Large Telescope, have found that it is leaving our solar system faster than expected.
The first time we discussed it, we were saying, oh my God, we really need to check and double check and make really sure, because the effect is so small and so subtle that many things could go and screw up your measurements. And after checking and double checking and cross checking, the effect was still there.
But astronomers might have already found an intriguing explanation to this observation. Oumuamua first came to the attention of astronomers by the end of 2017. Observatories around the world discovered that the object was a lonely voyager from interstellar space, the first of its kind to be observed.
So for the first time, we had evidence of an asteroid, an object that was coming at a very high velocity into our solar system, and the velocity was so high that it proved that the object was actually coming from the outside. It was coming probably from an other solar system and was just passing into our system.
Astronomers using ESO's Very Large Telescope and other observatories have shown that this peculiar object is moving faster than the laws of celestial mechanics predict. A result that caught the scientists by surprise.
We considered really various. One of them is an interaction with some magnetic field, or another one would be an interaction with a force going along the trajectory, not really knowing what it would be, just to see if it works, or a force that would be an impulse, like a small outburst or things like that. And all these hypotheses fail.
The most likely explanation for Oumuamua's odd behavior is that it is outgassing. Outgassing occurs when sunlight heats up the surface of an object. This causes it to vent a plume of gas that acts like a booster rocket. However, outgassing is a typical behavior of comets, which now leads astronomers to suggest Oumuamua is an interstellar comet rather than an asteroid. However, Oumuamua shows no trace of typical cometary features. The interstellar visitor does not show a characteristic long tail of evaporating material. It also shows no evidence for a coma, an envelope of gas and dust surrounding most comets.
In terms of the quantity of dust and gas that is released, it's tiny. It's really not much, but it's very small, so you don't expect a lot of dust. And still, again, comparing with normal comets, it's about right for such a small comet to have so little gas.
Astronomers speculate that perhaps the small dust grains adorning the surface of most comets eroded during Oumuamua's journey through interstellar space, with only large dust grains remaining. A cloud of these larger particles would not be bright enough to be detected by ESO's VLT. The true nature of this interstellar nomad may remain a mystery. Oumuamua's recently detected gain in speed makes it unlikely that we will be able to accurately trace its origin. And as it is getting further away from Earth, it becomes too distant for even the best telescopes in the world to observe.
We've never observed a comet like that before, but it's possible. We've never seen one, so many differences, many things in common, so we really need to wait for the next one to start making comparisons.
So the hope is that in the future, with better telescopes, more telescopes searching the sky for asteroids, we will find more of these objects.
But what we have learned from Oumuamua surprised us beyond our wildest imagination.
We're back for Asteroid Day from ESO Supernova, Garching, Germany. I'm Daniel Skuka. We're going to continue our program today talking with Detlef Koschny, and we're going to talk a little bit about, next we'll talk a little bit about some of the missions that have actually gone out and met up with asteroids and indeed brought back some samples. Detlef, a couple years ago, JAXA, Japan, flew a mission, Hayabusa 1, that went out to an asteroid, Itokawa, and actually grabbed some particles, some bits of the surface and brought them back to Earth.
Yes, that was another fantastic mission, a fantastic technical achievement. We have a few of these grains, they're just dust grains, very small dust grains, in our lab at ESTEC, and are analyzing these grains right now.
What are we trying to learn? What's some of the science behind studying these grains?
We're doing something very specific. We're looking at the charging of these dust particles. So, you know, electrostatic charge, people know if you take a cloth and rub your cat, then, you know, you get this discharge. Yep. That's what we're looking at for these dust particles.
Right. Just a few days ago, actually a couple of weeks ago, we had a chance to send our colleague Sean Blair from ESA Web TV into the labs at ESTEC to talk with the team there studying the particles from Hayabusa 1. Let's take a look.
This is Sean Blair reporting for ESA Web TV. I'm here in a clean room store in ESA's ESTEC Technical Center in the Netherlands, and kept within here are a few tiny pieces of some of the rarest, most precious material imaginable. It's come a very long way to get here.
Japan's Hayabusa spacecraft was the world's first mission to retrieve samples from the surface of an asteroid and return them to Earth. It nearly didn't make it. Launched in 2003, Hayabusa was damaged by a solar flare during its trip through space, finally reaching the rubble-pile asteroid Itokawa in late 2005. In 2010, unsteerable by the end of its 6 billion kilometre journey, the crippled spacecraft approached Earth's atmosphere like an asteroid, breaking apart. Hayabusa's sample container, however, was heat-shielded and parachuted back to the Woomera test range in Australia. Until scientists retrieved the small container, they had no idea if it actually had any asteroid samples inside it. And when they opened it, they still had no idea at first. It seemed to be empty. But scraping the sides of the container, followed by detailed scanning with an electron microscope, revealed 1,500 tiny particles that were of extraterrestrial origin. Extremely precious, these Hayabusa grains have become the focus of intense scientific study around the world. And 3 of them are currently here, at the European Space Agency's ESTEC Technical Centre in the Netherlands.
I'm here now in the lab with space environment researcher Fabrice Cipriani, who's been leading the study of the grains. So Fabrice, where did they come from? How did we get them here?
Well, actually we built up a consortium made of researchers from ESA and also from teams of INAF in Roma and the Partenopea University in Napoli, to propose an original study focusing on the electrostatic properties of those particles.
And that's different from usual. Normally people are interested in what the materials are made of rather than what they
exactly. So most of the studies are aimed at measuring the mineralogy, composition, basically the fundamental ratios of compounds which helps to date back the grains from the origin of the solar system, etc.
So what's the focus of your research?
Asteroids do not have an atmosphere, and as a result, their surface is directly exposed to incoming fluxes of charged particles coming from the solar wind, coming from the sun. So those charged particles, they deposit charges into the material. Asteroids, outer surfaces are layers of very fine particles, which dimensions ranging from microns to centimeters typically, which are held together by gravity, but also by cohesion forces. And on the other hand, they are a bit loose due to the acceleration, due to the rotation of the body, but also due to those electrostatic forces which are repelling particles from one another. And the focus of our research is very towards understanding a bit more or characterizing a bit more this type of interaction, electrostatic interaction, and the impact of those interactions in terms of regolith structure is that, for instance, the porosity or the density of the material can be a bit different from what we think it is if we do not include this component of the forces. So
what do the grains actually look like?
First of all, they're very small. Well, the samples we have are about 10 micrometer or 20 micrometer in diameter. The Hayabusa samples go up to several hundreds of micrometer, but we have very small ones. Also, when you look at them, they have a very inhomogeneous structure. They are very sharp edges. This is because they've not been weathered by water, eroded by water like on Earth, or friction together in the same way as Earth's particles are. And also you have micro cracks on the surfaces, so they're not like one block, they're cracked. And also you have micro craters or nano craters actually on them, which is also a witness of the fact that they've been exposed to the outer environment, a bit like all bodies in space, or planetary bodies in space have craters at their surface.
What do you do to them to test them?
Yeah, what we do is try to reproduce a bit what we have in space, although we can't reproduce, for example, solar wind in the chamber, but we try to bombard them with electrons and measure the amount of charges which are accumulating on the surface and how those charges distribute on the surface. And this is something which has never been really measured at this scale, at least on asteroid material. There was some testing done on Apollo samples. But in fact, because we don't have a lot of, well, actually we have very few of those particles, we also play with more standard material, which are like lunar analogs, for instance.
Like simulants.
Like simulants, lunar simulants, exactly. And we can at the same time play with full layers.
What's it actually like to work with the grains themselves? You have to be very careful, I guess.
Yes, we are we are extremely careful. From the time we received it, we've been thinking for quite a long time, I would say maybe 2 years, of developing a method which allows to handle them in a safe way, preserving at the same time their outer shape, because unlike indeed what most laboratories do because of the type of measurements, we do not want to embed them in some aerogel, or we don't want to press them into a support and then cut them to investigate their internal structure.
And you want to give them back to JAXA?
Yeah, indeed. So what we aim for at the end of the study is to safely bring them to give them back to JAXA. So hopefully, when we due to this method of handling, they will not have been altered or destroyed by our analysis technique.
Right. Well, thanks Fabrice for showing this around, and indeed thanks to JAXA for being so generous in the first place.
The good news is these grains might become a bit less rare in future. A follow-up JAXA mission, Hayabusa 2, is currently in space, due to return with more asteroid samples in late 2020. This is Sean Blair for ESA Web TV, signing off.
Following on the fantastic scientific results coming from Japan's Hayabusa 1 mission, Japan, JAXA, the Japanese Aerospace Exploration Agency, is actually flying a second mission, Hayabusa 2, which is going out to another asteroid, this time to asteroid Ryugu. And indeed, it arrived there just this week. We're speaking now with Con Kayal, who is working for Telespazio Vega with the German Aerospace Center, DLR, and you're actually based in the Mission Operations Center in Cologne for the Mascot Lander. And the Mascot Lander is going to be you're going to send the lander onto the surface of an asteroid. That's incredible.
That's true.
That's amazing. Con, thank you for joining us today. Could you give us a little overview of what's happening with the mission and what's happening with your Mascot lander, a European lander on a Japanese spacecraft? And of course, you just arrived this week at asteroid Ryugu.
Indeed, we are very excited. It is just on Wednesday that Hayabusa arrived at its home position, and now we are preparing for the landing. We have to choose a point where we are going to land, and then in October the 3rd, that's the plan, we are going to land.
That's incredible. Now, the Mascot lander, what is it? It's another satellite. What exactly, how big is it? What's its shape?
It looks like a shoebox, and it has about the size of a shoebox, so 20 centimeters. It has no landing gear, it has no thrusters. Wow. It is going to fall on the asteroid like a brick, actually.
Wow.
That is planned this way.
Okay.
And once we touch the ground, we will bounce a few times because we don't have a landing gear.
Okay, I think we've got a video we can bring up.
Yes.
And maybe we can show our audience just a little bit of how this is going to look when it actually happens in real time in October. If you just sort of basically talk us through what happens with this bounce. It's incredible that you're bouncing something onto an asteroid.
Right. On the video, we already see how Hayabusa is going down, descending. That will be, of course, much slower than on this video. And here we see it is getting lower and lower. And there's a spring that is going to eject the mascot. Now it's going to happen in a few seconds. And with at about 5 centimeters per second, that's the speed how we get away from Hayabusa. Now it is falling like a brick, as I said before. And we don't know how hard the soil is, but if it is hard, it's going to bounce as you see here. It will roll, and at some point, it's going to come to rest. And once it is not moving anymore, we are going to start with measurements. We have 4...
Yes? Come to rest, but how do you know which direction it's going to be pointing up? How can you
yes, there are
control that?
Sensors and there are proximity sensors.
Okay. What happens if you're completely upside down?
That can happen, and for that we have a mobility mechanism, and this mechanism can flip us again, turn us, or in the worst case we can even make a bigger jump until we get to mascot to the right side, looking to the soil.
So you're basically letting a hopping, jumping, shoebox-sized robotic explorer bounce on the surface of an asteroid.
Yes.
Good stuff.
If the soil is very soft, then it will not go.
Then it won't bounce. It won't bounce quite as much. What are some of the scientific aims of putting this mascot lander onto the surface? What do you want to find out?
We have 4 scientific instruments. Now we see the camera. There is a magnetometer. It will measure the magnetic field of the asteroid. MARA is a radiometer that is measuring the temperatures of the asteroid and how they change during day and night time. So that tells us something about the thermal inertia of the asteroid. And there is also this microscope. It's called micro-omega, and it is also a spectrometer. It can look at very small structures because it's a microscope at grains and then tell us their chemical composition.
Right. Now, we're going to spend the next few months not exactly orbiting asteroid Ryugu, but somehow keeping up with it.
Hayabusa stays between the sun and the asteroid.
Okay, and it actually needs that for solar power.
That's the so-called home position.
Right. Later on this autumn, when you found the spot that you want to deposit the mascot lander, you're actually going to do that in October, and you're going to be in Japan for that.
I personally will be in Japan, not in Cologne. And I will do basically communication between the control center in Cologne. With my, I might have 2 headsets actually at the same time on my head, one with talking to Cologne and one talking to Japanese colleagues in the Hayabusa control room.
Right. Now, of course, as with many complex missions, it's an international effort. What's it like working with some of the colleagues from JAXA from Japan?
That's of course extraordinary for me. I never worked with Japanese before. And I am fascinated how much they have accomplished with so few people.
Good for them. Good for you.
Yes.
Well, we're certainly looking forward to some great results from Hayabusa 2, from the mascot lander. There are some additional other landers that it's deploying, and of course it will be trying to grab a sample again and bring a sample back. So that's going to take some time, but this autumn we'll be looking forward to seeing you bouncing across the surface of an asteroid. Colin, thank you very much. Yeah, thank you. Good, thanks, great. Right. Okay, just flip the page here. And next one is we're going to actually pass over now to my colleague Tanya, our co-moderator, who is just behind me, back over on the other side of ESA Supernova, and she's going to talk with Olga Popova about Chelyabinsk.
Thank you, Daniel. And yeah, what an exciting journey for Hayabusa 2. And obviously we send missions to asteroids sometimes, but sometimes asteroids also come to us. And I'm delighted to have here today Dr. Olga Popova, who is a Russian scientist and an expert on one of the most memorable asteroid events from the modern generation. That's the Chelyabinsk event. So welcome, Olga. Thank you for being here.
Thank you for the invitation to join this amazing event here in Asteroid Day. And I'm glad to remind you how the Chelyabinsk event looks like. We have 2 videos with the spectacular superbolide. It was superbolide, it was so bright, it was brighter than the sun near the trajectory. And it was observed over a wide lens. It was seen from, 700 kilometers, for example. And on this video, first of it is from 200 kilometers, and the second one is from closer positions just in Chelyabinsk city itself.
Or what exactly happened in the event?
In fact, the asteroid came into the atmosphere. It was broken essentially due to atmospheric action on it. It was disrupted on numerous number of pieces, and it deposited most of its energy in the atmosphere, and some remnants of the asteroids came to the ground. The object initially was about 20 meters, and it is, 7-floor building, yeah? Just imagine it. And the most part of its energy was just in the atmosphere. Only small parts of the object came to the ground, and we collect materials there.
Yeah.
But nevertheless, it's tiny, tiny part, smaller than 0.1%, for example.
Okay, so these are meteorites that you found
Yes,
from the
we
Chelyabinsk.
found meteorites.
What was it like for the people there? I mean, were people frightened? Did they know what was happening? What was it like as an experience?
Because it was early morning, We have a lot of evidences, we have a lot of videos there, and we can hear what people were saying when they saw this object, this bright spectacular event. Some of them were thinking about airplane crash, rocket crash, but some people really get the point they said about cometary or asteroid impact, so they know what they see. The event was very spectacular, and people was going closer to the window or just outside to look on it, to look on this impressive dust trail which still was in the air. And at that time, minute or 2 minutes after the event, it depends on your distance to the trajectory, the shockwave came. And the shockwave pushed the glasses and scattered them. Also, light constructions were damaged. The shock waves acts on people. People were in panic in some places, and it also moved people down. For example, they fall
so
sometimes.
knocked them over.
Yeah.
Wow. So how many people were injured?
In fact, this day and next one, of about 1,600 people came to hospital for medical assistance, but it is a lower number. We have done few population survey by phone and through internet, and we got an imagination that about 10,000 of people were injured. The most injuries, of course, came from these glasses, from bruises. People got concussion, and they also have some eye hurts due to this bright radiation.
Oh, so their eyes got
Yes,
damaged.
yes, eye was damaged because the event was very bright, and also some people were sunburned because the fireball radiates in ultraviolet region. So some of them closer to trajectory, of course, have some sun burning in February.
Wow. Okay.
Yes, it was.
So you mentioned it was a superbolide. What does that mean?
In fact, standard is for superbolide, the object should be brighter than -17 magnitude. It's brighter than moon, and so it's quite bright.
The name relates to how bright the object is.
How bright is the object.
Yeah.
And as I said before, the most part of the energy was deposited in the atmosphere during the entry, but nevertheless we have these meteorites. And people have possibility to search for these meteorites as we have clear weather without no fresh snow at that time. And people were searching through the fields trying to find these pieces, and they found a lot in fact.
Do you know how many? Or?
Oh, it's difficult to estimate. I know that many locals have their own meteorite collections now. Yes. And the largest piece came to the lake of Chebarkul and produced a hole there, 7-meter hole. And there was first attempt to extract the object from the ground of the lake in the February. It was not successful. So a special campaign was organized. In October, this largest piece of about 600 kilograms was extracted from the ground.
Wow.
But as I said, all these meteorites is only a smaller part of initial object.
Yeah, sure.
Yes.
And scientifically, I mean, you did modeling of the event, and what can you tell us about that?
Yes, definitely. And we have some representation of our model. We put just how the energy is deposited along the trajectory, and this shockwave is developed, and it came to the ground and caused all these distractions, all these actions on the people which we observed.
Yeah.
And just later we will see how close our modeling corresponds to the natural observation.
Okay, wow, yeah, very close, yeah. So I think a lot of people would imagine that from such an event that the injuries would be direct from the impact or the pieces, but it's not, it's actually a shockwave. Yeah.
Yeah, but really for this scale event, the two main factors are dangerous. It's thermal radiation and the shockwave. It's two main.
Yeah.
And we had the same for larger event, for famous Tunguska event.
Yeah, sure, yeah.
Because it is the reason why we celebrate Asteroid Day
today,
June 30.
And we have the modeling from that as well.
Also modeled the Tunguska. And Tunguska was much larger than Chelyabinsk. It was, I don't know, maybe 15 meters across.
Okay.
And it plays a lot because this object was destroyed during the atmospheric entry and deteriorated there. The shockwave came to the ground, but all materials was strewn through the trail back to the atmosphere.
Oh, okay.
So we have no Tunguska meteorites at all.
Oh, wow, there's nothing left from the Tunguska.
Left. Yes, only burnt trees, fallen trees, and so on. And we were lucky, Tunguska was in small population area at that time. But nevertheless, there were some inquiries. We just go through all eyewitness accounts from that time, and we saw that there were a lot of concussions and maybe even 2 deaths connected with this event.
Yeah.
It was maybe due to panic or something like that.
And having an event like Chelyabinsk and so much video footage, because I'm sure lots of our viewers would have seen on YouTube the videos and from the cars and things. So being able to study an event like that, how does that help us in terms of thinking about future potential events?
Yeah, for sure. Because now we know that this event we need to be aware of before, yes? We need to have some warning to people, just not to go outside probably near constructions, not to go to the windows in order not to be injured by them. So yes, we know that this event is dangerous now.
Yeah.
Because before, no one was thinking that this 20 meters event is dangerous. It was thought to be extremely safe.
Yeah.
No one was worried about.
Okay, so it's in some ways it's good that it happened.
Yeah, in some sense.
Great, thank you very much. Now we're going to head back to Daniel now. Thank you for being here, Olga. I think you're staying around. If people have questions, remember on social media, you can ask ESA or ask ESO. And we want to have your questions, and Olga would be able to answer any if you had any later as well. We're going to head back to Daniel because we're talking about impacts and asteroid impacts, and we've already said previously that the dinosaurs, lots of scientists think the dinosaurs were wiped out by an asteroid impact, but we're going to go back to Daniel on the other balcony, and he's going to show us a clip which shows their research into how the dinosaurs actually became extinct.
Thank you, Tanya. So we're back with, we're continuing with Asteroid Day from ESA Supernova in Garching, Germany. I'm Daniel Skuka. There's a pretty important event that took place something like 66 million years ago, and we haven't gone into too many details on that one yet. It was an asteroid that impacted Earth, and let's face it, it's the big topic that everyone is wondering about. And of course, we know it wiped out most of the non-avian dinosaurs. The incredible creatures which roamed the Earth first appeared during the Triassic period between 243 and 233 million years ago. They went on to become the dominant land species, yet they are gone, and we are here. And we've done a little bit of research into this situation, and today, for the first time, we are pleased to present the top 10 reasons why the dinosaurs went extinct. Let's take a look.
So there you can see some modern day research about the dinosaurs and why they may have gone extinct. For those of you who have just joined us, welcome to our ESA webcast for Asteroid Day. We are here live in the ESA Supernova in Garching, just north of Munich. We've been on now for just around about an hour, and we have another hour left. You'll be able to watch it on replay as well. It'll be on both the ESA and the ESA websites for you to take a look at afterwards. Now, I'm here now with Dr. Timo Prusti, who is the project scientist for Gaia from ESA. And Gaia, this is the model behind us that you can see. Gaia is a fantastic space telescope. Timo, could you tell us a bit about the general mission of Gaia?
Gaia is really a cartographer. So we are mapping the stars in our Milky Way galaxy. So we are really map makers, so that astronomers can navigate where they have to go with their observations. So we tell where the stars are, but not only that, we also tell how they move. So we can look a little bit back in time, a little bit in the future, how the sky will look.
Excellent. And how many stars are we talking?
It is an incredible number of 1.6 billion stars. I mean, somebody may say, isn't it a bit too much? But we have to remember, it's still only about 1% of the stars in our Milky Way galaxy.
Okay, but still a huge number of stars. But it's not just stars, is it? We're on Asteroid Day. It's not just stars that Gaia is mapping. What else is Gaia doing for us?
Yeah, it is true. So very early on we already realized that we can also observe asteroids, we can also observe quasars. But talking about asteroids, they are a little bit difficult for Gaia because they are moving with respect to stars.
Yeah.
So we have to do a little bit extra effort to catch them, but we do. And we have just made the first release of asteroid data with as part of our Gaia data release. And we have the positions and orbits for more than 14,000 known asteroids.
Wow, 14,000 asteroids. And so these were asteroids that we knew about before, and they were targets. So you'd selected them already as targets for Gaia.
Well, actually, Gaia is very democratic. We don't select anything. It selects it by itself.
Okay.
And these 14,000 have been just caught when they have been, Gaia have been scanning over them, as well as some 300,000 other asteroids. What we have done a selection at the moment is that looking for the data reduction, we have selected these 14,000 and looked in more detail to them in order to learn how do we treat the rest of the asteroids, the full set of 300,000 asteroids.
Okay, and so what are you measuring with respect to the asteroids? What are you able to do with Gaia?
So the Gaia power is twofold. We are measuring the positions extremely precisely. We can really pinpoint how these asteroids are orbiting around the Sun. That is going to be a unique set of data from Gaia. But it's not the only thing. We are also measuring with so-called spectrophotometer the energy distribution of these asteroids. So what can we do in the very simplistic way? We can look which of the asteroids are light, which of them are dark.
Okay, so like the brightness of them.
We measure the brightness and also as how it changes from red color to blue color, how the brightness changes, and that will give us a handle into the properties of these asteroids.
Okay, so before we could see some, I think it was the maps of the orbits, and there was lots of red and orange colors. Could you tell us a bit more about those orbits and what we're seeing on that picture?
So the orbit picture, we have, you have indicated there is the Sun in the center, and most of the asteroids are orbiting between Mars and Jupiter. And we have two populations. You can see two colors there. One are the red ones and one are the orange ones. And it tells that they have different properties. So one of the things that we can do with Gaia is that when we look these precise orbits, we can look where are precisely the dark asteroids and where are the faint ones. But you can see more in this picture. You can also see a black gap. And this is something which is due to Jupiter. It is such a big planet that it is disturbing the orbits, and effectively it cleans out this region of asteroids.
So is that due to the gravity of Jupiter?
It is the gravitational forces which do that. On the other hand, you see a very narrow band of red orbits at the same orbit where Jupiter is. And these are locked into the same orbit with Jupiter. They are not close to Jupiter, but they cannot also escape.
Ah, Oh, okay, so they're not locked like the moons of Jupiter orbiting Jupiter, but they're locked in their orbits around the sun.
Correct.
Yeah. Okay. And why is it important to measure these orbits so accurately? Why is that important to the study of asteroids?
We know asteroids are really old objects, and they have a message in them. They have the message of how our solar system is born. And by looking this message and interpreting it, it can tell not only how our solar system is being built up, but also our understanding how solar systems in general around stars are building up.
And in terms of the future for Gaia, I mean, we've got 14,000 that we've managed to map accurately. What is Gaia? How long is Gaia going to be active for? That's one question. And then what's the plan for the future as well?
So we have now been operating for 4 years, and like all spacecraft missions, at some point you run out of fuel. Our fuel is rather specific one, but we will run out of it in 6 more years, so 2024. And what we intend to do the remaining time is actually we are just measuring the same things on and on again, and in the end we will get a orbit for 300,000 asteroids.
Wow, fantastic. Thank you very much for being here, Timo, and I believe you're going to hang around as well in case there are any questions. For now, thank you for being here.
Thank you.
So we've heard about Gaia, that's a space telescope. We're here at ESO's Supernova, and ESO and ESA work very closely together in the field of asteroid detection and characterization. And one way that has been done is actually that ESO telescopes have been used to map Gaia's position, and by mapping it accurately, we can then make better observations with and the measurements with Gaia. And I'm now joined by Dr. Susie Ramsey from ESO. Susie is the ELT project scientist, and I'm delighted you're here. Thanks for coming, Susie.
Thanks very much, Tanya. That's great. Thank you.
So can you tell us a bit more about some of the ways ESO's telescopes are used to sort of supplement and complement the work that ESA's telescopes in space do?
Certainly. Happy to do so. So I think one of the things that's been emphasised in some of the clips that we've seen today already is that a satellite like Gaia that scans the whole sky is absolutely perfect for discovering asteroids. But then the next thing that we want to do is to take a much more detailed look at these faint objects and to try and work out what they're made of, to look in more detail at how they're moving across the sky. And to do that, we need a larger telescope. Now, launching a large telescope into space is difficult to impossible. Luckily, ESO has, in its observatory in Chile, 4 of the largest telescopes in the world, the so-called VLT with their 8-meter mirrors.
Yeah.
And these telescopes are equipped with a broad range of instruments, which are the tools that astronomers use to understand the asteroids in more detail.
So when we say instruments, we mean cameras or spectrographs or detectors of that sort. So we use that general term instrument to describe those things.
Exactly.
So what sort of instruments have we got on the telescopes that can be used?
So they split into 2 main categories. We have imagers, such as the FORS instrument, which was actually one of the first ground-based instruments to observe Oumuamua. And with imagers like this, either in the optical wavelengths or near infrared, we can take pictures in different filters from which we can get an idea of the composition. By observing night after night, we can see actually if the brightness of the asteroids is varying, and then this tells us something about how they're rotating as they move across the sky, all of which are critical to really understand what they're made of.
Yeah.
So that's the imagers. Now, to look in even more detail and understand what they're made up from, then we want to use our spectrometers. And the spectrometers take the light from the asteroid and they spread it out, like when we spread out sunlight and we see a rainbow.
Yeah.
So actually on the screen you can see what is actually a spectrum, we would call it, rather than a rainbow, a spectrum of the sun. And what we don't see with our eyes is the dark stripes that are in that spectrum. And the precise position of these dark stripes is characteristic of the precise chemicals that are in an object.
Okay.
So this is the sun, but we can use the same technique for galaxies, for stars, and of course today for asteroids such as the ones that we've been talking about.
Yeah. So you mentioned Oumuamua. Now, something quite special happened there with the Oumuamua because it was this object from outside of our solar system, and ESO telescopes were used. What happened there? Can you give us a bit of an insight about the...
Okay, so I think this is really, I mean, Oumuamua was such an exciting object. It took everybody by surprise. We barely dreamed of discovering such a thing. And so we have a special way of working with the telescopes in such cases. So normally we plan everything in advance. We want to be very efficient. So 6 months in advance we know our program for observations with these professional telescopes. When something like this happens or a supernova goes off, then we go into target of opportunity mode, and that means astronomers can write to ESO and say, okay, I've discovered this, it's essential that I get more observations soon because it's fading, as in the case of Oumuamua, moving away from the sun, and then we can take observations even as quickly as the next night. So we stop everything, we drop everything, and we go to the target. Yeah. And that's exactly what happened. Yes.
Fantastic.
Then of course we carried on observing it, which was the point at which we discovered it was not an asteroid.
Yeah.
Which, for fans of asteroids is disappointing, but for scientists, I love this. I think this is how science works. We observe and we're prepared to revise our understanding of the things that we observe.
Yeah.
It's very important.
So you've mentioned a bit about some of the instruments on the telescopes at Paranal, for example. Are there any other telescopes that we use for asteroid detection and characterization?
Something quite exciting at the moment is how we can use ALMA. Now ALMA looks very different. This is a sub-millimeter array of satellites. They look like your TV dish. Actually they're observing at sub-millimeter wavelengths. So shorter wavelengths than radio telescopes, but somehow similar. They look very similar. Now, when we're observing with the VLT, then we're observing reflected sunlight from these asteroids, and that's basically how we see them. With ALMA, we actually see the very faint emission that comes from the asteroids themselves. So it was recently used to observe Juno, and it's just seeing the thermal emission, the heat coming from this very faint object. So we see directly the surface. So this gives us a whole new tool for understanding asteroids.
Fantastic. Yeah. And you are the ELT project scientist. So ELT is the extremely large telescope. So what's the future? What is ELT going to do in the realm of asteroid characterization?
So yeah, at the moment we are actively working on building this new telescope. It will be ready for astronomers in 2025. And we're making sure that it will be capable of observing asteroids. We think that we're going to want to carry on doing this a long time in the future, especially when we see the results coming from Gaia. So yes, it's simply that. We make sure that we have this ability to do the targets of opportunity, to interrupt the observing. We make sure that we have instruments which will be able to detect asteroids, and with the ELT we'll get down to even smaller and fainter objects than we can now. We can study new populations of objects in our solar system with the new telescope. Because it's such a big mirror. Yes,
so collects more light. Yeah, exactly. Great. So yeah, I find it fantastic that these collaborations happen, and that's the way science works. One organisation can't do everything on its own, and they work very closely together to build up.
The world, internationally.
Exactly. Yeah. Thank you very much, Susie.
Thank you.
I think we're heading back to Daniel now on the other balcony, but I'm not sure. Possibly not. I've forgotten. Okay, that's good.
Some of the ESA telescopes that are being developed, although I must say I'm really impressed with telescopes. They're amazing, and those are amazing. Over here in Europe, though, ESA is working on some telescopes that are called fly-eye telescopes. A little bit smaller, but still very important. And we're going to use those to look for asteroids. Detlef, what is a fly-eye telescope?
Well, the fly-eye telescope is indeed a bit smaller than what we just saw. We talk about 1 meter effective aperture. The focus for this telescope, why it's different, it has a very large field of view. It covers more than 100 times the apparent size of the moon. So with one single exposure, we map a very large area in the sky, and that will help us finding all these asteroids out there which we don't know yet.
Now basically you want to be able to use this telescope and in future several more like it to actually scan the whole sky each night. How will that work?
With the field of view that we have, it's roughly comparable to a normal pair of binoculars, only that There our aperture is much larger. With this field of view, we managed to scan with one telescope about a third of the night sky 3 times. We need to look at the same area in the sky 3 times to see a moving object. In the end, we hope that we get 3 to 4 telescopes which will let us scan the complete night sky once every night.
And this data, when we get these images, we're doing the scanning, we get this data, we're actually sharing this data with effectively the rest of the world, but we're doing that in a certain way. What
happens directly at the telescope is that the data is processed and we search for moving objects which will then be detected as such, and we will inform the Minor Planet Center about those very quickly. The complete images will be made available to the public, the scientific community, but we need to transfer them back from the mountain first, and that may take some time because we talk about so much data.
Right. But the Minor Planet Center, that's the IAU, International Astronomical Union Center, where all astronomers all over the world send their sightings of asteroids.
Positional measurements of asteroids are collected by this Minor Planet Center, and this will also happen with the data that we will generate.
Right. We had a chance recently to send Kelsey from ESA Web TV down to Milan, where the telescopes are actually being built right now by OHB Italia, and Kelsey had a chance to actually see the telescope under construction and talk to the team there doing the construction. Let's take a look at what she saw.
Hi, I'm Kelsey Brennan-Wessels for ESA Web TV. We join you from Milan, Italy at OHB Italia, where a new high-tech telescope to detect asteroids is being built. Let's take a look. This is the Fly-Eye telescope in production, which isn't what we usually picture a telescope to look like. Traditional telescopes have a narrow field of view, which makes hunting for threatening asteroids a slow and tedious process. But the Fly-Eye has 16 individual cameras, mimicking the structure of a fly's compound eye, to offer an extra-wide field of view of 44 square degrees. With this field of view, the telescope will be able to detect asteroids at risk of hitting Earth in as little as a week in advance. So, how does it work? Lorenzo Cibin at OHB Italia gave us an up-close look at the machinery.
We can see here the full optical instrument connected to the ground support equipment, and then you can see here the central ring of the instrument that hosts such a lower part is the primary mirror. Kelsey, if you look there is a B-shaper that do a repartition of the field in 16 channels. This is, for example, one channel with the camera, CCD camera, and this CCD project a portion of the sky.
An additional 3 telescopes are foreseen to be produced and placed in complementary locations around the globe to increase coverage and improve the efficiency of the network. Once this first Fly-Eye telescope is completed, it is destined for Mount Mufara on the Italian island of Sicily.
The telescope has to be mounted, has to be associated to an equatorial mount. The equatorial mount is a particular mount that allows to avoid that during the exposure time the stars track, and the stars in this way remain fixed in their position when we take a picture from the telescope.
And while the telescope is taking its pictures, it's important that the structure is very stiff in order to reduce vibrations that could blur the image and thus reduce the capability to detect very faint objects in the night sky. And remember that to learn more about space, about asteroids, or about the Fly-Eye telescope, you can visit our website at www.esa.int.
Wow, what an incredible piece of technology. It looks like that thing is trying to detect alien spaceships, but of course it's optimized for finding asteroids. Detlef, not only the hardware is important, building telescopes, but also working with astronomers is extremely important, working with astronomers worldwide. Very recently, just last month, you had a chance to organize a workshop here in Munich where you could bring together astronomers, asteroid experts, researchers working in the field of asteroids from almost all over the world here to Munich and talk about asteroids.
Yeah, I was lucky enough to be part of a team that organized a workshop which lasted for 4 weeks, which is a long time in our field. We brought together typically 45 asteroid researchers in any given week in these 4 weeks. And you know, we know that the risk of being hit by an asteroid is quite small, but we also know that we do need to know more, that we do need to learn more. The only way of doing that is to find out where do we stand in the scientific field all over the planet. This was our chance to do this in this workshop.
We actually had a chance to visit you during the workshop and interview some of the participants on camera and actually ask them for some of their answers to some of the open questions currently being talked about in the field of asteroid science.
Asteroids are these tiny dots of light moving across the sky, and if you just look at them in one image, it looks just like a star. Knowing the orbits of asteroids is important because we want to understand where they are in space. That tells us if one is going to impact the Earth.
I think that the biggest challenge is associated to the fact that attached to an asteroid orbit there is always an uncertainty, there is always a probability.
So we have to get many nights of observations, at least 2 observations in each night. And preferably we do this for 3 nights in a row. And then you can say, hey, we found an asteroid, we have an idea of its orbit, we think we know where it's going next.
Usually you can make, for example, examples out of your everyday life, like, for example, to being hit by a lightning twice in a year, which is, of course, something doesn't have a high probability. So somehow the asteroid population is formed by different sites. It's a bit like when you have a pot that is crashing on the ground, then there are a few big pieces, some medium-sized pieces, a lot of small pieces, and then powder everywhere. More or less, that's what we are talking about. There are a few big asteroids, and this means that the associated risk is not that much because it will happen very rarely, and then they are big, so they are somehow easier to spot them in the sky. What we are really concerned is let's say the small to medium size. This means objects of the order of a few tens of meters, because these are the ones that are more likely to actually enter the atmosphere, and they, even if they will not threaten our civilization, but they can produce damage. Maybe even let's say 1 week before they can become dangerous. But this is enough. For example, in Chelyabinsk in 2013 there was this 18 meters object which exploded in the sky, and it was coming from the direction of the sun, so our telescope were blind. But for the asteroids, it's something that we can actually, in effect, predict. So why we do not know it? Why we have to talk about probability and not certainty?
A warning would be issued if there is any object that is believed to be bigger than 10 meters and that has a chance of hitting Earth which is bigger than 1%. Independent of when it is, then you would issue a warning, not more. If the object is a bit bigger, 20 meters or larger, and it could impact within 20 years, then there is a recommendation that maybe one should start to look at possibilities for civil protection.
When we talk about deflecting asteroids, we're talking about, for example, impacting it within a spacecraft. You know, you just take, that's the simplest way, you take a spacecraft and you just slam it into the asteroid. And by slamming it into the asteroid, you give it a push, which will either speed up the asteroid or slow it down, and thereby changing the orbit of where it will be in space at a later time. Other methods is also, for example, the one that everybody really likes is that if you have a nuclear bomb and then you explode it, you can, for example, explode it off the surface of the asteroid. And then the explosion itself, it's vacuum, so there's no pressure, but you can have the radiation. and the radiation will go into the surface, and then it will kind of splutter the surface, and that will create as if it's a rocket. So it will push the asteroid. Or you can land on the surface and thereby also getting the pressure from the pressure wave of the explosion, and which will also push it and change the velocity of the asteroid. There's also methods for if you have small asteroids or if you have more time, where you can just take a spacecraft, for example with an iron engine, one in each end, and then you just push these iron particles onto the surface, and this small pressure will over time, months and years, will give enough push to the asteroid to change the velocity of it and therefore its orbit. Are we obliged to actually do a space mission? Let's say your own country is going to get hit. Are you obliged to deflect the asteroids? That's one question, but are you now obliged to help your neighbor? If your neighbor can't afford or don't have the technology to deflect an asteroid. There's also the question of whether, if you get information about an asteroid, that's going to impact. Are you legally obliged to tell this information out? Morally, you are, definitely.
So it's really hard to communicate the risk, communicate the level of risk to the public.
I frankly, I do not have a recipe. I try and have a conversation with people all the time, when I talk with the media, when I talk with just my friends and anybody I meet randomly. I just try and have a conversation with them to try and explain how infrequent it is. So I think that, unfortunately, we're all used to disasters like hurricanes and tornadoes, tsunamis. We hear about them, we read about them in the newspaper all the time. And unfortunately, they can be quite common and they can kill a lot of people. But we never hear about asteroid impacts killing people.
One aspect that we discussed this morning was about the need of having, for example, an index, a very easy index to communicate to the public the danger associated to different kind of close approaches. For example, an index like the one of the electrical appliances that tells you whether a close approach is close enough to the Earth to be considered a danger or not.
Suppose that I say that there is an asteroid that will hit the Earth with a probability of 10 to the minus 5. What does it mean, 10 to the minus 5? Well, let's put it like this. Suppose that you're in front of a railroad track and you have to cross it. Of course, you wait that the train is not passing. But let's make this experiment. You are now blind. I will use any device for not letting you feel when a train is coming. You're in front of the railroad track. You have 1 year to decide when to cross, because one train is passing only once per year. If you cross, I'll give you 1 million euros. Of course, I do not have 1 million euros, but let's do it. This experiment. Would you do it? This experiment or not? Somehow the real difference between us and the dinosaurs is that we are posing our questions about what the asteroid risk means. What is the asteroid hazard? They didn't have this chance. Don't ever ask a dino what asteroid hazard is. What we know is that that space is not as empty as we were thinking. Let's put it like this. But now, if you go to the space calendar, it's full of flybys of asteroids. So what has changed? Do we have more risk than before? And this is not at all, because this means that they were flybying the Earth the same before, but we were not seeing it. Now we have surveys which are devoted to finding NEOs. This is the ability of science to see what is invisible.
Detlef, you obviously had an excellent workshop with people coming from all over the world. For you personally, what was the biggest takeaway, the biggest result that meant something for you?
I think you said it already. The people came from all over the world. We asked them afterwards, what do you think about this workshop? What did it give to you? Well, just like asteroids don't care about boundaries, about city or country borders. This is what happened here. We brought together the international community. We started new collaborations, and that will push our field of asteroid research dramatically.
Good stuff. We now want to take a little bit of a pause. We asked you earlier on the webcast to post your questions using either the Ask ESA or Ask ESO hashtag. And we've been keeping our eye on Twitter and Facebook. We've actually gathered quite a list of questions, and we're going to pass over to Tanya just behind me. And remember, not only with your questions for Ask ESO and Ask ESA, if you happen to see a dinosaur at any time in our webcast, you need to post a photo, and you need to use the Spot Sophie hashtag over to Tanya.
Thank you, Daniel. Hi, I'm joined again. We're still live here in the ESA Supernova for another half an hour or so, maybe less. So I'm joined with Timo, Susie and Olga, who were all on screen earlier today. And yeah, we've been getting some great questions, so thank you very much for participating via social media. And yeah, I have been slightly distracted by the possibility of presence of dinosaurs in the building, so I hope you've been keeping your eyes open for Sophia. So let's start the questions off. Thank you very much for participating. The first question I had is for you, Timo, and this is from Buddha Help. And the question is, how many near-Earth asteroids have been discovered so far?
So there is a count, and the count at the moment is above 18,000. And the count is increasing every day. On a typical day, I think there are like 3 more near-Earth asteroids discovered. So the list can be followed live, almost, how the additions are coming.
Okay, and so when we're saying near-Earth asteroids, just to remind ourselves, what do we mean by near-Earth asteroids? How near are we talking?
Well, I think it's a very wide concept, but it is close to Earth, obviously, but because we don't know so precisely the orbit, so we have to be a bit careful and expand our view of what is a near-Earth asteroid, because we want to know more precisely those ones which might be dangerous for the Earth.
Sure. Thank you very much. Hope that helps you, Buddha Help. Now I have another question, which I think this one is probably best for you, Susie, perhaps. So this one is from @Ryar. And so hopefully the biggest eye in the sky, so the ELT, can spot an asteroid with 400 meters diameter before it would impact Earth in the coming years. So the question is, if we were to turn the ELT towards an incoming asteroid, would it be able to track and observe it? Great question.
Very good question. Okay, so I think I might give a bit of technical background so that everybody understands the question. So as we heard from the Gaia talk, asteroids don't move in the same way as stars do. Right? They move a different way across the sky. It's partly how we detect them. So, of course, telescopes, they spend most of their life observing stars and galaxies, and so they just track the way we're used to seeing these star-filled pictures of the stars moving across the sky as the Earth rotates. So in order to be able to track an asteroid, we have to program the telescope to behave in a slightly unusual way. Now the ELT will do that, we're making sure that it will do that, but we're making sure that it can track to detect the normal sorts of asteroids and solar system objects that we know about. So for fans of numbers, this is about 200 arc seconds per hour. This is 200 arc seconds is about a 20th the size of the moon. It's very small. So of course, as asteroids would come nearer to the Earth, with the possibility of impact, then they're very likely going faster than that. So we'll be able to see them when they're quite far away, which I think is good. Maybe and we'll be able to measure the orbits very precisely. So we'll be able to predict when they, with high certainty if they're likely to impact the Earth. But actually tracking them when they get close to the Earth, I think we can't swing our 42-meter giant telescope around the Earth quite fast enough, unfortunately. That will have to be for smaller telescopes, which as they get closer, they'll get brighter, so that's probably fine.
Okay. Thank you very much. Hope that was helpful answer for you @Ryar. Now, a question which perhaps all of you have a bit of input to. This one comes from @DSL Synth. And so one of the interesting perspectives of asteroids in the future is the potential of space mining for precious metals. How certain can researchers be about the composition of asteroids without visiting them? Who wants to start that off?
Well,
you still have the microphone.
So keep talking about my telescope, my favourite telescope. Of course, mentioned already that one of the ways that we understand the composition is by doing spectroscopy, and for the faint objects we need the big telescope. The bigger the telescope, the better the spectrograph, the better we'll be able to detect actually the composition. But for things maybe buried in the asteroid, I think that's not really going to work, and then probably that's where we need to work, as we are already doing with our ESA partners, to help out there.
Yeah. Timo, do you want to add to that?
Yeah, it sounds almost like something that you have to go there and dig, and I think there are already plans and ideas how to achieve that one, and of course it's always the matter of there are lots of ideas, and how do you find the funding to do your dreams and do this examination.
Yeah.
I would like to add that, in fact, we need to have three types of observations. We need to observe from the telescopes the surface properties, and we need to go there to take a sample and to study the interior, because the interior could be very different from the surface as we know now. And we need to continue the study of the objects which enter our atmosphere, trying to extract asteroid properties from this entry, similar as from Chelyabinsk, for example, about the strength, about the structuring, and other properties of those.
Maybe it's good to remember that, of course, we're apparently quite successful at landing things, right? We did well with the Rosetta mission.
Yeah, definitely. That was amazing.
Okay, maybe it wasn't perfect, but we got some fantastic results. Very provocative statement. So we know how to do this, right? The prospect is there.
Yeah, great. Thank you. Hope that was a good answer for you. Another question here. So thinking a little bit about Oumuamua. This was an object from outside of our solar system, but we have a question from @PaulBrownIT, and he asks, in what circumstances could an asteroid from our own solar system go interstellar? So what could cause some object in our solar system to be ejected?
So you need something to disturb it, and so you can imagine many ways to how to disturb it. One thing what we can do, and I'm referring now to Gaia, is that we can know very precisely how stars are moving. So what we can do is that we can look in past and also in the future which stars are going to go very close to our sun. And there seems to be we are fine for millions of years, so there is no panic. But there will be stars passing by in the future, and that may cause disturbances. Maybe to asteroids it's very difficult because then you need a very close encounter. But we have lots of comets further away from the sun, and that is a place where a disturbance can actually these comets to be disturbed and sent away from our solar system, and then somebody else in another solar system maybe detects them.
When our solar system was first forming, things were a lot more chaotic, and could there have been collisions then that might have sent things out of our solar system, or would they still, everything that was created, was it still in our solar system now?
I think that is a topic where the details we don't know, but for sure that kind of scenario is possible, that lots of material is not just bound to the newly born star, but can leave the system already early on.
Yeah. Great, thank you very much. Now, let's have a look. We've got some other. I've got a question here. Now, maybe one of you will understand this a bit better. Not my field of expertise, but a question here from @Lars W.H. Ohm. How strong is Oumuamua compared to 67P? Is strong a term used with comets that I don't know about? I'm not sure.
I can say, because of course it was such a hot topic when it happened. So what we did with Gaia immediately, can we see it? And so, no, we couldn't. It was far too faint to our telescope. So in that sense, it is a very faint object. It was very difficult to observe, and luckily these telescopes were able to do it and get the knowledge what we have heard about earlier in this program.
Okay. Thank you very much. That's all we've got time for in terms of the questions. Thank you all very much for your answers and contributions. I hope the people whose questions were addressed are happy with the answers they got. And we're going to head back to Daniel now on the other balcony with Detlef.
Thanks, Tanya.
Thanks, Daniel.
Thank you, Tanya. Detlef, Japan is not the only space agency out to an asteroid. Indeed, ESA is working on a mission called Hera, which is going to go to a double asteroid, a binary asteroid, and work with an American mission called DART to see if we can actually deflect an asteroid against a future contingency?
Yeah, this is a mission study which we are actually currently performing. The idea there would be that NASA impacts an asteroid. We go to a binary system, we hit the smaller object, and then from Europe we would build a mission called Hera, which goes to that particular asteroid and observes the effect. We would look at the impact crater, how big is it, we would characterize the mass of the object, and that would teach us a lot about the way we could deflect a real asteroid.
And in addition to the primary deflection demonstration mission, we're actually going to be able to do some science, some plus alpha science with this mission as well.
Yeah, we have a lot of what we call bonus science there. We will be the first mission that ever goes to a binary asteroid. So far all spacecraft have been just looking at individual objects. It turns out asteroids tend to come in pairs. There's many more of those than we initially thought. We now know about 15% of the asteroid population is binary, and that of course in itself is a cool scientific topic.
Right, we've got a video that we can play out for our audience, and maybe you can just talk us through what we're seeing in the video, and it gives us an actual overall profile of how the Hera mission should unfold once it actually gets into space.
Right, here we see a video of the mission. So, well, as we just said, it's all about protecting our planet, making sure that we can do something if an asteroid were about to hit our planet. We would only want to do that once we have demonstrated that we can actually really do it, and that's what this project is all about.
There's the impact.
That's the American part, and you see here the effect. The white asteroid on the left was the object, as it were, before the impact. When you hit it, you actually move the orbit a tiny bit, and now you see the European spacecraft approaching, and it would observe the impact crater. The size of the impact crater is very important. It tells us something about the energy that we deposit in the asteroid, and it could also determine the mass of this object. We can measure the deflection actually from ground-based observations, but if you don't know the mass precisely, then that's rather useless. So that's why we need the second spacecraft there. It uses a suite of instruments, so we can look at the surface of the object. We can say, well, is it a porous surface? Is it a very solid surface? All of these things are important to understand what's going on. We just saw the ejection of what we call CubeSats. These are very small satellites, just 10 by 10 by 30 centimeters each, and they will give us additional possibilities to measure, for example, from 2 different locations or even 3 different locations, and characterize this object even better than with just one spacecraft.
Wow, this is an incredible mission. Now, where are we right now with the development of this of the ESA Hera mission?
On the European side, this is currently still a study, and we are finalizing the design of the spacecraft. So by summer next year, we will know precisely what we have to build. And then at the end of the year, ESA will go into its next budget round, and there we hope that we will be approved all the funding that we will need for this mission.
Right. Now, as I understand it, asteroid deflection is a very important technique to demonstrate, because if we ever find an asteroid coming towards us that could cause some damage, we'd want to be able to possibly push it away.
It depends a bit on the size. If the object is small enough, you could argue, well, let's just take the hit and evacuate or warn the population. But indeed, if the object is 50 meters or larger, you would want to deflect it to be really safe.
Right. Now, Detlef, we've talked a lot today in our webcast about robotic missions, going out to asteroids and doing all kinds of incredible things. But actually in the future, we really want to be able to send an astronaut to an asteroid, a human mission where an astronaut can actually explore an asteroid, do some science that a robotic mission can't do, and potentially even look at something like asteroid mining or future exploitation of asteroids.
Well, if you want to know more about that, I'm really scared about rockets. I wouldn't want to sit on a rocket, so I would suggest you should ask an astronaut.
Good idea, and indeed that's precisely what we did. Just a few weeks back, we had a chance to speak with ESA astronaut Luca Parmitano. He is a European astronaut coming from Italy. He's flown already one time to the ISS. He did a 6-month mission, and he's now training for his next mission to the ISS, launching in July of 2019 next year. And the second part of his mission, he'll actually take over as commander of the ISS. And we actually had a chance to talk with him and ask him what he thought, how he feels, how he foresees a future human mission, which hopefully is not that far into the future. Let's take a look. Good.
When humans finally fly to an asteroid, they will need the same skills that they do now. They must be able to use technology to perform science and exploration. However, there is something more. They're going to need some new technology. Initially, we're going to have to be able to find these asteroids, so very precise guidance and navigation. Then we're going to have to park close to an asteroid without hitting it, and that's going to be something that needs to be developed. And thirdly, once the humans need to go on the surface of the asteroid, they're going to need new spacesuits capable of anchoring themselves onto the surface, because such a small gravitational field is going to be very, very hard to explore. So some of the technologies that I just talked about are partially available today. We do have spacesuits, but we must be developing new ones in order to be able to perform the kind of tasks that are going to be necessary for exploration and exploitation of an asteroid. And for the spacecraft, we already have navigation system. We already have, for example, our spacecraft to the International Space Station. But in the future, this new spacecraft will have to be able to do that when connected to a completely unexplored little world like an asteroid. Space is an inherently risky environment, and obviously flying to an asteroid is going to present all the same risks that you have flying in space. And everything that is in the unknown is always an increase in the risk. Today, we are preparing for these missions using analog environment. One of these environments is called NEMO, the NASA Extreme Environment Mission Operations. It's where we stay underwater in a small environment for 2 weeks in a habitat that's called Aquarius, about 20 meters underwater. When we are in this environment and we stay there for the whole time underwater, we perform the same tasks that we would perform on an asteroid, and we take advantage of the neutral buoyancy of being underwater to simulate the microgravity environment that we would find on an asteroid. Nowadays, when we perform our missions on the International Space Station, it's a very known environment that was designed to be used with handholds and specific places where we can anchor ourselves in order to operate. When we go to an asteroid, we won't have any of those tools. We are going to bring our own and to install them in order to be able to explore and navigate around the asteroid. When we land one day on that asteroid, the lucky person is going to feel something that has never been done before. He's going to be standing on a very, very tiny world with a very small horizon, rotating in the universe. It's going to feel that the whole universe is rotating about you. And I think that that's part of the beauty of it, that we just don't know what it's going to feel like.
Welcome back to the final scene of our webcast from ESO Supernova in Garching. We're just about at the end of our webcast. We're out of time. And I certainly want to thank all of our guests who joined us today in live at ESO. Timo Pristi, Suzanne Ramsey, Olga Popova, Tanya Johnson, Sophia the Dinosaur, Detlef Koschny, and Ken Kayel. I'm Daniel Skuka. We had a fabulous time. Thank you very much for watching today. Big thanks also to everybody in ESA Communication. Big thanks to everybody in ESO Communication. Everybody did a great job. We had a lot of support from behind the scenes that you don't get to see. And of course, we had a lot of support in social media. Thank you very much, everybody, for watching. If you've seen a dinosaur, we want to see that screenshot. Post it with Spot Sophia. And from all of us to all of you, Happy Asteroid Day! Thank you very much. Oh, good. Thank you very much.